So in this video, what we're going to do is we're going to turn to one of the most important modeling techniques, which is multiple regression. And through this multiple regression, what we're able to do is incorporate a whole series of independent variables in order to predict or understand the behavior of a dependent variable. So multiple regression is a pretty big topic, and what we're going to try to do in this particular presentation is a little bit more limited. And what we'll start by doing is taking a look at the ideal weight versus height relationship that we looked at earlier and tested with techniques such as analysis of variance. And we'll look at how we might create a model which is slightly more useful out of that data. Then what we will do is we will do a survey of an automobile and a series of features. And in many respects, one of the ideas behind this survey was to illustrate some of the pitfalls of regression. And when we actually conducted the survey in the workshop, I found pitfalls that I hadn't even imagined would occur. What we'll then do is interpret the coefficients of that model, and we'll talk about some of the issues that may have caused the model to break down. We'll then talk about some of the limitations of regression, both in the context of the models we did and more generally. And then finally, we'll talk about some variations on regression, which we will not actually demonstrate, but which we will talk about. So, just as a refresher from the last session, let's think about what we did with ANCOVA. And what I'll do is I'll bring up JSP. I will then open up our cleaned height and weight data. We'll come over to analysis of variance, go into ANCOVA, and our dependent variable was the ideal weight that individuals put in. We were particularly interested in seeing if gender was an effect there, and what we wanted to do then was control for height inches, because we know that the genders have different average size, so we're just trying to isolate the gender effect from the height inches. And what we found when we did this is that gender, the top row, was significant at 0.001, and height in inches, the controlling factor, was also significant. Now, what didn't this tell us? Well, among the things it didn't tell us were what direction the relationship was in, how impactful it was on our measurements. All it told us is that there was a high probability that the male and female samples came from processes with different means. And so this is fine for hypothesis testing, but from the perspective of a model builder, this was not terribly useful. So what might be a more useful way of presenting this information? Well, what we could do is we could create models that would allow us to predict ideal weight. And we're going to look at two very simple models, and these are called linear models because what we're going to do is predict ideal weight as the sum of a coefficient associated with height and a constant, and then that is the first model. So to express this as an equation, what we're going to say is ideal weight is equal to some constant plus some constant that we're going to determine from our data times the height of the individual in inches. So if we wanted to express this in equation forms, y, the dependent variable, our ideal weight, is equal to a constant plus this another constant times the height. Now, that would be another way of expressing our hypothesis, and we could get more sophisticated if we actually wanted to look at both gender and height. We could create a new model, and in this model we would have a different constant plus a different constant times height plus a different constant times gender, where 0 is male and 1 is female. It doesn't actually matter which you choose, but it will affect the sign of this constant. So expressing in terms of x and y, our dependent variable y is equal to a base constant plus a constant times x height plus a constant times x gender. And these models are more useful for a manager than the pure hypothesis test because they actually allow us to predict ideal weight as opposed to just telling us that gender affects what the ideal weight is. So let's see how we could go about building this model, and what we'll do is we'll bring up JASP with the same data set loaded, and we will choose linear regression. The dependent variable is the ideal weight. The height in inches is the covariate for our first model. And what JSP does when it does a regression is it also includes an analysis of variance. So I'm going to just move this over so we can see the results here. And so we still have the analysis of variance telling us that it's likely the means are different. But then we see the regression model itself. And what the regression model says is that our coefficient C0 is 303 or negative 303. And what we do is then multiply the height in inches by 6.75 or thereabouts. And what we see here is that both of these have a p of less than 0.001, so these are both significant. So what we can do is we can put this into an equation and say we wanted to predict the height of some, or the ideal weight of someone who's 72 inches. Well, we take minus 303, the constant, our C0, plus 72, which is 6 feet in inches, times 6.75, actually 6.752, but you get the idea, and that gives us a prediction of 183 pounds. Now, if you want to test yourself, what you might want to do is figure out the predicted ideal weight for someone who is 5 foot 5 inches. So you'll have to convert the 5 foot 5 inches into inches, 65 inches, and then you just fill in the same formula here using 65 instead of 72, and that should give you a predicted ideal weight from this very simple model. What is nice about multiple regression, however, is we're not limited to a single independent variable. We can actually do our two-variable model, which uses both height in inches and gender as a way of predicting. So I will bring up JSP again. What I'll do is I'll come over here to the model, and all I need to do is add gender to our covariates. And now what we see is that we have a new three-variable model where suddenly our C0 has changed. It's now by about minus 138. Our height in inches is now multiplied by 4.46, and then we subtract about 33 for gender. And what that means is, because we set 0 as male and 1 as female, is that we could predict that a woman's ideal weight for a given height is likely to be about 33 pounds less than the same ideal weight prediction for a man. And if you take a look at the significance here, all of the coefficients are significant. The constant is a little weak. It's a 0.059, but for our model's purposes, it's probably a lot better to leave that constant in than to toss it out because it's not significant. Because it's a pretty big factor. Our constant subtracts 137 pounds. So if we wanted to incorporate this into the model, what we would do is, if we had a 70-inch woman, the projected ideal weight would be the minus 138, which is the constant, plus 70 inches, which is what, 5 foot 10, times the 4.46 here, minus 33 because it's a woman, and that gives a prediction of 141 pounds. Now, how would this change for a man? Well, the only thing we need to change here is that now our C2, our minus 33, is multiplied by 0, so we get rid of the minus 33. So now the 5 foot 10-inch man would be 141 pounds plus the 33 that we earlier subtracted, so that would be 174 pounds. So when we're interpreting a regression output, what are some of the key things we need to look at? And I would argue that there are 3 basic elements that you're typically looking at when you're interested in regression models. The first of them is a measure overall of how good the regression is, and this is R squared and adjusted R squared. Now, what the R squared is basically a comparison of how well your regression predicts the individual observations as opposed to just using the average. So for every observation, we have an error between what our model predicts and what the actual value is. The easiest way to do that, the most naive way, is to take the average value of your dependent variable and just look at how far each observation goes from the average, and we square each of those differences so that both negative and positive differences become positive, and that gives us an overall variance. What we then do is we then use our model and we make the same predictions for each observation, and we sum the squares of all of those errors, because our model is going to have some errors too. The way R squared works is if your model is no better than the average in predicting values, which would be pretty unusual, then what it's going to do is it's going to give you an R squared of 0. If your model predicts the values perfectly, then it's going to give you an R squared of 1. And so essentially when we say that the R squared is 0.778, that means that we're predicting about 78% of all the variance as opposed to just using the average. So we're about 78% of the variance is handled by our model, which is pretty good. In the social sciences, it's not unusual to have R squareds in the 0.2 range, which is to say your model explains 20% of the variance, but 20% is better than nothing. Now, one of the problems with models is that because the computation has a number of parameters to work with, essentially your coefficients C0, C1, C2, and however many coefficients you use, what happens is that as the number of coefficients approaches the number of observations, the model becomes relatively useful, because if you have the same number of coefficients as you have observations, you can get a perfect fit. So there is a value called adjusted R squared, which basically is always a little smaller than R squared, and it reflects the fact that you lose a certain number of degrees of freedom when your number of coefficients approaches the number of observations. As long as your number of observations is a lot larger than the number of coefficients you're trying to compute, then the adjusted R squared and the R squared will be pretty similar as they are here. If you get to a point where you have 9 coefficients and you got like 12 pieces of data, then your adjusted R squared is going to be a lot lower. So that's a measure of overall fit, and in a certain sense, that doesn't really tell you much more than, say, an analysis of variance would. It gives you a sense. It doesn't tell you how the model moves. It just says it's not terribly bad at predicting. Now, the next thing that's important is these p-values. And as we've talked about, whenever you're looking at research, you always want to take a look for p-values, because that's basically the way the statistical model from being used by the researcher tells you whether or not your data is pretty much random. And if you have a high p-value, a p-value of 0.5 or something like that, it's telling you, your estimate is really no better than random. There's, a 50-50 chance that that the coefficient might actually be 0 instead of what you think it is. That's a little bit, that's not a completely accurate description, but you get the general idea. What the p-value does is it tells you the likelihood that you'd end up seeing this coefficient from random data versus the likelihood that you'd see it from data where the actual value is the coefficient. So in the case of this particular model, what we see is that our coefficients for gender and height in inches both have very low p-values. That tells you that we can be pretty sure that women actually predict a lower ideal weight for themselves than men do, and that height in inches does in fact matter when you're predicting ideal weight. Now our intercept, the constant that we need, is the p-value is 0.059. That wouldn't even hit our 5% significance test, but nevertheless we need it for our model. If you could in fact create a model that forces the constant to be 0, and then you're going to get different values for your coefficient for gender and height in inches. But in this particular case, typically you want to keep the constant in because you don't really expect your model to go across the entire range of data. We would not expect this model that we've developed to work for someone who's 6 inches tall or for someone who's 120 inches tall. But within the range that we were looking at, say between 5 feet and 6.5 feet, our hope is that the model would work pretty well. And because it's a linear model, what we're doing is we're fitting a straight line to that data. And in fact, if you were looking at this from a medical point of view, a straight line fit might not be the best model to use. You might want to use a model such as a body mass model, where what you're trying to do is reflective of the fact that as your height goes up, chances are your width increases proportionally and your depth increases proportionally. So you might very well expect for your weight to go up kind of with the cube of height increases as opposed to necessarily going up linearly. But over a small enough range, a line can be an approximation. And that's what we've got here. And our R squared tells us it's a pretty good approximation, all things considered. Now the next few slides in the slide deck deal with the survey of automobiles, and I am not going to walk through the process of cleaning up the data from the survey here, but what I will do is review the survey itself, and then I might create a separate video for cleaning up the survey if there's a strong interest in that. And so what I'm going to do here is I'm going to load up the survey and then just identify it. The basic premise is that you've got your daughter has done very well in school and you're going to buy her a new car, and your daughter has already settled on the color of the car and on the model of the car, and so what you're interested in is two things: what cars are available in the lot, and what would be the ideal car that you would order. And this is a little bit contrived, and we'll see some of the problems of that when we actually look at the data. But the notion here is that we have 6 cars on the lot with the same model and color that's desired, but they have different sets of options. So the first one has upgraded sound and a rear view camera. The second one, upgraded sound, a rainbow interior, no rear view camera. It has floor mats, a moonroof, a turbo engine. It's not a demonstrator. The next one has a rear view camera, floor mats. It is a demonstrator. The next one has an upgraded sound system, a rear view Notice that this is the same as P4. And when we talk a little bit more about the notion of validity, this would be an example of something that we could be using to test the reliability of our survey. P5, upgraded sound, floor mats, turbo engine, and P6, rainbow interior, turbo engine, so forth. What the survey then asks is for you to price each option in dollars. So that is, there's one of these for each one of those options. And then at the end, what it asks you to do is it asks you to create a custom configuration and just check off all the elements that you would want in your ideal configuration, and then put in the maximum amount that you would pay for that combination, and we'll call that the preferred car. And so we're actually getting the data in two different ways. We're getting the data with respect to a bunch of preset models on the lot, and then we're asking you to design your own car and identify what the maximum that you would pay for it is. So we'll be getting the data from that particular data set. And then the next thing we would do is we would download the results. Here's an example of what the results look like. I created an analysis spreadsheet that you could then use to bring it in. And then I go through the process of extracting all that data. And that way we have the ability to create both a preferred car and a standard car set of data. And what we'll end up doing is combining them for reasons that will become clear shortly. So one of the things I was hoping to do with this data set is illustrate some of the limitations of regression, because once you have a data set with a dependent variable and a bunch of independent variables, it's almost irresistible to go into multiple regression. Even if you step back and thought about it, you decide maybe this doesn't make sense. And so there are a number of problems that we run into when we load your data. And by the way, these problems we also ran into with my test data. So what I'm going to do now is I'm going to open up JSP, and I will open up our available car data. This is the one for the 6 available cars, which means that we got 6 observations for each individual because you had 6 different cars that you selected. So we'll bring this up. Then we'll come over to multiple regression, linear regression. What we're trying to predict here is price. That is the independent variable. That's the dependent variable. And then our independent variables are these dummy variables, 0 and 1, representing the various factors, such as whether or not it's got a rainbow interior, backup camera, upgraded sound system, and so forth. So we stick the covariates here. And one of the things that we discover when we go into the regression, and let me just adjust this thing so that we can actually see all the results, is that we have a problem. And the problem is that 4 of our variables, or 3 of our variables, we simply cannot use. And the reason we can't use them is that when the computation is done to compute the coefficients, in this case it would be C0 is the intercept plus C1 through C7, 1 for each of the variables. When we do the computation for that, it's critical that you cannot tell the value of one of the variables based upon the other variables. That would be called linear dependence. And if you have linear dependence, you can't do it. And the reason is the mathematics can't figure out whether to attribute the effect to the coefficient that we can predict or the other coefficients. So it's essentially the same reason that when you create dummy variables, you always have to have one less dummy variable than you have choices, because otherwise, if you had 7 choices and 7 dummy variables, if you knew 6 of the choices, you would automatically know what the 7th was. So it's the same problem here. Well, in this case, basically I would have had to give you 7 independent choices in order to make sure that all the coefficients could be determined. In fact, I gave you 5 because of the 6 choices, 2 were identical, and so there were only 5 combinations, which means that you could figure out the values of 04, 06, and 07 from combinations of the other things. So what we would need to do if we actually wanted a regression would be get rid of, say, 04. Now we're just missing 06 and 07, so we can get rid of 06. Now we can get rid of 07. And now the regression is okay, though the results do not necessarily make a huge amount of sense. 01 was the sound system, and apparently, based on your pricing, you'd pay $3,000 plus for a sound system. 02 was the rainbow color selection, and apparently you'd pay $2,200 for this, and we'll later find out that that's definitely not the case. 03 was the backup camera, and apparently they would have to pay you $835 for a backup camera. Now notice this is not a significant coefficient, so we could argue, well, we shouldn't have that in the model. And then 05 is, 05 is the moon roof, and apparently you'd have to be paid to take on a moon roof. And notice that these coefficients are significant, which tells us there's a real problem. We also see the adjusted R-squared for this model is 0.23, which is not a very good value, but on the other hand, I've seen a lot worse in published papers. So as a result, we got to say this model does not look very good now that once we've taken out the variables that we could predict. So our 6 standard models made things a little bit messy. So now we think, well, what about our preferred model? Maybe we won't have that problem of linear dependence in the preferred model because you're creating your own choices. Everybody must, have different choices. So we shouldn't be able to predict the value of one from the other. So let's basically take this, do the same thing. We'll go in File. We'll take the preferred car variable, we'll get this in, we will go into regression, linear regression, we will make price our dependent variable, we will take our various independent variables, bring them in, and now we get another error. It says least square regression model is undefined. The independent variable 02 contains all the same value. The problem with that is if nobody wants 02, then we don't know what would belong with 02 and what would belong with the constant, so it simply cannot do the regression. 02 was the multicolored interior, and apparently nobody wants the multicolored interior, which is interesting because in our previous regression of standard models, the multicolored interior actually had a pretty high value with a high significance. So that's kind of odd. So what I'm going to do is I'm going to move this one out of our model, and then with that we've eliminated the linear dependence. Notice the R-squared is still relatively low, 0.267, but there's a big difference between the adjusted R-squared and the regular R-squared, and that's because we've got 6 variables, we only have 27 observations, and so we're starting to get down to the point where we got too many variables to fit the observations. Now if we come down here, let's see what the coefficients tell us. What I'll do is I'll bring this thing over. So if we take a look over here, what we see is the intercept, okay. By the way, our intercept should be somewhere around 20,000 because what I told you was that you were satisfied with a $20,000 base price. So ideally, if the value of all the options was 0, you'd have around a $20,000 intercept. Now, we see here is all of a sudden we will pay $2,000 for a backup camera, but we got to be suspicious there because this is not a backup camera. $2,000 for a sound system, but you see this has a very low p-value. I mean, this has a weak p-value, 0.267. So we probably would want to toss that one out. Similarly, the backup camera has got a poor p-value, so we probably take that out of the model. On the other hand, 04, the floor mats, has a good p-value, 0.027, and basically we're saying we would pay nearly, $3,700 plus not to have floor mats. That doesn't seem very likely. 05, the moonroof, not very significant at all. 06, the turbo, not significant. 07, not significant. So this is a pretty lousy model. Indeed, the only thing that's significant really within the model itself is the fact that we really hate floor mats. So our preferred pricing doesn't seem to be a really good model either. So what are we going to do if, one chunk of our data has linear dependence, the standard models, and one chunk of data has a variable that's all zeros? How can we address this? Well, one thing we might end up having to do is combine the two models. In other words, since the data is in the same format for both of them, and it came from the same data source, we might decide that we want to try to combine the two and see what happens. So that's what we're going to do next, and what we'll do is we'll open JSP, and I have already created a combined data set. So we bring that in, we go to multiple regression, linear regression, we set price as our dependent, we set the 7 dummies as our independent variables. And we've still got an R-square of 0.267, adjusted R-squared, which is about the same as our preferred model, but we didn't get any errors. So let's take a look at what this particular model tells us. So I'm going to bring us over here a little bit, and I'll scroll down. Maybe move this thing over. All right. So if we take a look over here, what we see is the p-value for the different variables. Well, not very good. Only a couple have really good p-values. Again, we really seem to hate floor mats. P-value 0.006. And we really like the turbo option, p-value 0.001. And so that would, in a sense, tell us what we're looking for. We also seem to, let's see, 05 is the moonroof. We're pretty close to liking the moonroof. So you might ask, well, how do you get all this messy stuff here? Well, one of the things that you might want to do is you might want to take a look at something like the correlation matrix of the variables, because if you've got variables that are highly correlated, sometimes they will impact the model, but they'll have very high values of p, suggesting non-significance, which is the model's way of telling you it can't figure out what variables to attribute the different effects to. So let's open up the correlation matrix and just see what we've got. So what we'll do here is we'll come over to multiple regression, correlation matrix, and we'll just plunk all the variables in there for the combined model. And here we have to slide this sucker over a little bit in order to give us a clearer view. So what we see is that there are some significant correlations with price, because price is going to be the top one. We see that the first variable, which is sound system, is positively correlated with price. The second variable, the color, the correlation is not as significant. The third variable, backup camera, not really correlated at all with price. The fourth variable, which is the floor mats, is correlated with price, fairly significant. The fifth value, which is the moonroof, is correlated with price. The sixth value is correlated with price, and that's the turbo. And then the seventh value is negatively correlated with price, and that's the demonstrator. In a certain sense, this particular thing looks better than our regression analysis, just looking at the correlation coefficients. But what we also see is a lot of these variables are highly correlated with each other, and that's going to make it harder for the regression analysis to actually perform effectively. So if you're actually trying to create a model with this, what you'd probably do is you'd probably take out some of the correlated variables and see if we can get a better model this way. But another thing that this illustrates is that really, you can't guarantee just because you can mathematically perform the regression that the regression values are actually going to be terribly meaningful, even if they're significant. And I ran into some of this when I was creating my own sample test data as well. So this is not just a problem with the data gathered in this classroom. So one of the things we want to do now is we want to think a little bit about some of the circumstances under which you might want to use regression and some of the circumstances under which the regression model probably won't tell you very much and might even mislead you. So after we did the regression in the workshop, we had a discussion, and I'll just try to hit some of the high points of the discussion and provide some of my thoughts on it. We already talked a little bit about why we can't include some variables in the existing models, and there are three reasons that we encountered. The first is the variables are linearly dependent, which is to say you can predict the value of a certain set of variables by knowing the values of the other variables. So if you've got linear dependence, you cannot use all the variables. In other words, you cannot predict among the independent variables, you cannot predict the value of any independent variable by knowing the other variable values. Another problem we ran into was simply that some variables did not vary at all. In the case of the sample, the preferred cars, nobody wanted the rainbow color interior, and you have my strong agreement with that. I cannot imagine anything uglier. But since everybody gave 0 for that, we could not attribute a value, whether it was positive or negative, to that. And when we remove it, whatever value that variable might have had is going to be included in the constant. The third reason is that variables are highly correlated with each other. If the variables are highly correlated with each other, then it's quite possible that you would not be able to distinguish which effect belonged to one variable, which effect belonged to another. So you might have a model with a pretty good R-squared, and yet two variables that were highly correlated might have relatively poor p-values because the model is telling you, hey, look, we can't figure out which effect is which. So these are the reasons why we might have to get rid of some variables in a regression model. Another issue is how well do these models fit? For overall fit, you'd probably look at the R-squared. None of these models were very good for the car. On the other hand, when we looked at the height, gender, ideal weight, we actually got a pretty good fit there. R-squared is 0.7, 0.8, that range, which says that those models probably are pretty good. The R-squared for the car model was, 0.26 or whatever it was. And a lot of times when researchers are developing models in the social sciences, they're much more interested in the individual coefficients, because the coefficients are something that you can use in your hypothesis testing. So you could make the hypothesis that individuals will pay more for a car with a moonroof, and then even if the overall R-squared of the model isn't very good, if you have a high significance for the moonroof coefficient, you can say, well, that's evidence that they will pay for a moonroof. That doesn't mean we're very good at predicting what they pay for a car as a whole, but it does mean that they would pay. There's significant evidence that they would pay for a moonroof. Another issue is, what are the most useful values in the results? Well, the most useful values in our particular results are primarily the p-values of the coefficients. From a research standpoint, that's telling you whether the value of the coefficient is significant or not. Mind you, even if a coefficient is not significant for a particular value, you can't just drop it from your model. You have to actually remove the variable from the model and recalculate, because things like the constant will change dramatically depending upon what variables are in the model. So whatever model you use, you need to incorporate all the coefficients regardless of their p-values. If you don't think a particular variable is significant, remove it from the model so it doesn't have a computed coefficient, and so you don't have effects mixed in with the constant. So that's sort of the bottom line there. $10,000 question, do the findings of this model make sense? And the answer is no. I really do not believe that people would pay $4,000 not to have free floor mats put in their car. And the reason for this is that one of the assumptions that you would get for data coming out of multiple regression is that all of our observations are generated from the same underlying process. And what these results tend to show us is that different people may have very different tastes, and when we combine all these people together in our observations, the regression isn't necessarily going to tell us very much, because it's forcing the assumption that all of our observations were generated from the same process, and in fact different people have different tastes, and so really they're not generated from the same process. And so the analysis in a certain sense doesn't really make sense, and then the findings don't make sense. Now, in a situation like this, we can readily determine by looking at the findings that they don't make sense. Nobody is going to pay $4,000 not to have floor mats in their cars, or whatever the ridiculous value of the coefficient was. But nevertheless, if you're dealing with research in areas where you do not have a lot of domain knowledge, you might accept that because the coefficient is significant. And so you really have to step back and ask yourself, is the results that we're looking at likely to be the consequence of a process which generates observations according to the same formula, or are we dealing with something fundamentally different? And the example I have used already is the notion of, say, mapping ingredients to a taste evaluation of all the recipes in a cookbook. Suppose we had a food critic who created a dependent variable, how much I like this, and we basically took an observation for every recipe in the cookbook with dummy variables for each ingredients. I guarantee we'd get some significances, and we might include with p.0001 that garlic has a positive impact on taste. But in fact, we know that's not the way the process works, because the ingredients strongly interact with each other. And if the ingredients strongly interact with each other, then when we talk about individual coefficients, it doesn't necessarily make sense. Part of the value of practitioner-focused research is that you should come into the problems you're looking at with a pretty good idea of what might make sense and what might not make sense. Obviously, you have to have an open mind about this, but nevertheless, I would say this was a survey that would be poorly designed. Now, we could have a similar type of thing where we actually were looking at the cost of cars, and we had a whole bunch of full cost values and different options for the car. Now, under those circumstances, presumably all the cars came out of the same factory, they're all generated by the same process. We might be able to come up with really good estimates of how much it costs to add a moonroof, or how much it costs to add floor mats, or how much it costs to put a backup camera in there. Because that process might make sense. But when we're dealing with process with taste, what we're looking at probably does not make a lot of sense. Would the analysis be of use to a manager? Well, because it doesn't make sense, we wouldn't necessarily expect it to be a lot of use. One of the things that you might get out of a survey like this is, well, since floor mats are most likely not the problem, what is it about the inventory that we had that caused us to have such a negative reaction to floor mats? So floor mats might be a symptom of some underlying cause that affected people on the whole, as opposed to being the end result. I'm speculating here. But I would say you would not probably want to use these results directly in a model, but because some of them are counterintuitive, you might want to look more deeply for explanations. And identifying things that are counterintuitive might be something that would be of value to a manager. Finally, how might the survey be better designed? Well, as I say, since people have different tastes, this would probably not be a great survey as it's specified. Now, what you might end up doing if you wanted to get people's impression of the value of these things, because that would be useful from a pricing standpoint, is you might add a whole bunch of variables that help identify, the age, the gender of the customer, where they're located, what types of outside activities do they do? Do they like to drive around as sportsmen, or do they mainly urban, or whatever, with the idea of trying to find out if different preferences cluster with different individuals. That might be useful, but that would require a lot more data. You're not going to be able to get that kind of data out of 26 observations, but if you had 260,000 observations, maybe based upon negotiations with dealers for buying new cars, then that might help you decide, okay, we're going to put cars with moonroofs in Massachusetts, but we're not going to put them in Florida because in Florida it makes people hot and they don't want to pay for it. Or, I'm making this stuff up as I go along, but that gives you the idea. But as the survey is currently designed, it basically takes people who are going to have a bunch of different tastes and it tries to create an overall model. And it's not clear that this would be useful for anything. So the bottom line is, when should you be really concerned about regression, or what are some of the things that you might worry about? And I'll tell you right off the bat, if I have data that looks like it would nicely go into a regression model, I'm going to tend to run the regression model because it's so easy to do. And just looking at the results might give me some ideas as to where to look further. But by itself, you've got to be very, very careful with regression models. And here are some of the concerns that we have. First off, you can have problems with your data. We certainly saw that. You might have correlated variables, correlated observations, time series data. We create a variable, say, a year and month or something like that. If there is a trend, that model is going to be a very good predictor. Variables that have trends tend to be very good, but the problem with that is all it's going to do is tell you that there's a trend, and it will also essentially say, well, if you don't know anything else, the best thing to do is just project according to the trend. But that doesn't give you any insights that you're not likely to have otherwise. And so you have to be particularly careful using things like regression models with time series data, where one of your independent variables is, some measure of time. Truncated scales is another issue. For example, I think I've mentioned earlier that something like 50% of the world's wealth is associated with 1% of the population. Well, if you have a wealth scale that for 1 very poor to 5 very wealthy, what's going to happen is that there's going to be a huge range within that very wealthy area, and so as a consequence, you can easily lose important data. And as I mentioned, with something that's distributed according to a power law like wealth or population of cities, you can lose some very important information about where most of your population or where most of your money is by creating scales that do not take into account the vast differences. Another problem that we sometimes run into is low clinical significance. If you get enough variables, you can often get very nice p-values, less than 0.01, for very tiny effects. And a lot of times those effects will be so small that from a practice point of view, it would not be worth trying to achieve them. On the other hand, from a hypothesis testing point of view, you could use them. And here's one of the ways in which academic papers sometimes diverge from what is useful to practice, because very often they're looking at very tiny effects. A successful hypothesis test is a really good starting point for a paper, but it doesn't necessarily mean it's going to be any use. Another thing is a failure of your underlying assumptions. In cases like wealth, which I talked about, the outliers may represent a very, very important part of your data. You see this, for example, in citations to research. There's one journal where 20% of the citations come from one article. That one article has been cited like 25,000 times, and 20% of all the citations to that particular journal, organizational behavior and decision processes, come from that one article. Well, if you toss that article out as an outlier, you're really having some impact on your model. We also will find that sometimes errors are not normally distributed. Remember, I talked about earlier how when you're dealing with averages, and regression deals with averages, if you have enough observations, the averages will tend to be distributed normally. The problem is enough observations could be very, very large if, say, your underlying process is a power law. So you may have errors that are not normally distributed. You might have errors that are correlated. This is very common in time series analysis, where the observation at t minus 1 is very correlated with the observation of t at 0, is very correlated with t plus 1, and so forth. Those all can undermine the regression. Regression's a pretty robust technique, which means even if the assumption fails, you often get something, moderately useful out of it. But if the assumptions are off too badly, then you have to be very, very concerned about variables that are kind of borderline significant. Finally, you're going to have a very poor fit with your model. Our model of the used for the automobile assessment was based on the notion that everybody has the same preferences. Well, that's a really poor fit with our model. In our height versus weight model, we took a process which is probably best modeled as a cubic or a square relationship, and we tried to draw a straight line through it. Also, a lot of times in a regression analysis, you'll see observations that are correlated but and high significance but aren't really causal. I think I talked about this in an earlier slide where I was trying to relate global temperatures to the consumer price index and found a really good model, better than the correlation between global temperatures and carbon dioxide. The difference is there's some science between the carbon dioxide relationship, whereas there's no science between the consumer price index. And actually what made me start looking at that was I heard that the price of stamps was very correlated with global temperatures. Well, that's also very correlated with the consumer price index and so forth. The point is that just because you see the relationships, you do not necessarily have any evidence of causality. And that's one of the reasons that you need to have underlying theory behind what you're saying, and why when you see something like people will pay $4,000 not to have floor mats, you start looking for better alternative explanations to the data. So I mentioned that there were some sort of special cases that we might be dealing with where the regression model isn't perfect, but where we might be able to do things to make it a little better. One example is if your model is based on percent changes, regression, except over a very small range, is not going to be that useful of the straight linear model. What you can, however, do is you can build a multiplicative model where essentially your model is that your dependent variable is some constant k times x1 to the c1 power times x2 to the c2 power times xn to the cn power. So that is basically a model where variables multiply together. Now that works out pretty well for percentage changes because a certain percentage change in one variable produces an overall percentage change to the model itself. Now, the way we can bring this into multiple regression is we can transform this by taking the logarithm of both sides. And if you remember logarithms, what happens is if a value is raised to a power, we multiply the logarithm of that value times the power, which becomes our constant. And if two values are multiplied together, we add their logarithms together. So in this case, if we take the logarithm of both sides, we get log y equals c0 plus c1. And of course, that just means if you take the logarithms of all your data, then what you can do is you can basically build a logarithmic model, which is multiplicative. And you can also do this with dummy variables because the log of 1 is 0, and so the log of anything else is some other value. So you can use 0 and 1 like this as well. And so this type of model sometimes is a better model when you're dealing with percent changes. And a lot of times you will see people take logarithmic models. Now, interactions between variables is another example of something that we talked about as being a big problem. You know, the ingredients in a recipe interact. Now, one of the things you can do, and you'll often see done as research, is they'll create what's called an interaction value variable by taking the product of two variables and adding that into the model. So you'll have the variable themselves, x1, you'll have the variable x2, and then you'll have a third variable, x1 times x2, which captures a lot of the interaction for two-way interactions. Now, this starts to break down when you have very complex interactions. When you've got 8 variables interacting together, there's no interaction term that's going to capture all that. You'd have to create your own interaction variables. And if you have lots and lots of interactions, then the basic model of regression, which is basically each variable has its own effect that can be added, is not a very good model. Now, a third case is the case of limited dependent variables. In this point, something like price, has a whole range over which you can go. But sometimes you might want to do an analysis of a go, no-go decision where there are only basically 2 possible values, 0 and 1. And there's a specific type of regression called logistic regression, which is different from logarithm. But logistic regression, which can be used for that, and I'll mention that in passing in the final lecture sequence. So if we look at what we want to accomplish in our second day, what we've done so far is we talked about fitting data to a curve, we talked about multiple regression, we've talked about some variations on regression, though we didn't actually do anything with them. Now what we're going to turn to is some other more complex ideas, and the idea of how to deal with many, many variables, and how to try to sort of abstract, say 25 independent variables into 3 or 4 meaningful combinations that we can talk about them in a sort of a sensible way. We'll talk about the question of how we assess the rigor of research and where our quantitative methods fall into that discussion. And then finally, we'll talk about some exploratory techniques where you basically have a lot of data available, and what you're trying to do is use quantitative analysis to see if it can give you any insights that you might not have had just by your own experience with the data. And that type of thing is becoming increasingly important as we deal with areas like big data, because big data involves data sets that often have hundreds of thousands or millions of records that give us plenty of opportunity to explore things that human beings on their own are unlikely to find.